Okay, we're going to get started on work. You have these notes in your packet. Until now, we've only seen systems where energy was conserved. So in other words, no forces were acting on the systems. A very, very common force to be acting on systems would be friction, and we've been ignoring it. So in real life, this is usually not the case. We're not going to be able to ignore it anymore. And we want to look at systems where total energy is not being conserved. In other words, the amount of energy at A is not equal to the amount of energy at B. What's happening with work? Energy is transferred out of the system and it cannot re-enter, or it can be transferred into the system. And systems where energy is not conserved have had work done on them. So all work is the transfer of energy. Because it's energy being transferred, the units are the same as the units for energy, joules. The symbol for work is a capital W, and the equation work equals FD cosine phi. Let me define what all of these are. So W is work, F is force, D is distance, and phi is the angle between the applied force and path traveled. So work equals FD cosine phi. If your angle phi is either 90 or really if it's only 90, then cosine of 90 is 0, so you have no work being done. If your angle phi is either 180 or 0, then your work is just a positive or a negative. So yes, you can have negative work. That just means energy is leaving the system. Positive work means energy is coming into the system, and we'll see that with the example. So since work depends on force, distance, and the cosine of the angle between the two, if any of those are 0, then no work is being done. And this is a little bit hard to conceptualize. So say I decide to stand at the wall and push on the wall, and I push and push and push and push and push, I work up a sweat, but the wall doesn't move. I did no work. So because the object did not move, because the wall did not move, there was no distance, therefore there was no work. And then because the cosine, I said this before, because the cosine of 90 degrees is 0, any force applied perpendicular to the object will do no work. So again, that kind of goes with me pushing into the wall. If this is the wall, I'm pushing on it and pushing on it and it's not moving. Not only is that force perpendicular to the wall, but there's no motion. So for two reasons, perpendicular force and no distance, there's no work being done if I push on the wall. Okay, and the last thing that we need to know about work are work diagrams. These are very simple. You're going to show the direction of a force with a solid line, you're going to show the direction of the motion with a dotted line, and you're going to indicate the angle between the two lines with phi. So let's say we've got a force being applied in that direction. Your work and let's say it's let's just make this a box. So a box with a force in that direction and it's moving across the floor. Your work diagram would show the force in the direction of the force, a dotted line indicating the distance, and the angle phi to show the direction of the force versus the distance. So work diagrams, very, very, very simple. And we just want to do them to show, we just want to draw them to illustrate what direction the force and the distance are. I'm going to do 2 examples. Again, these are pretty straightforward and simple, just how to use the equation FD cosine phi, and then the next video will cover how this applies to energy. So how much work is done by friction and by a person when the person pushes a 40 kilogram box a distance of 10 meters at a constant speed across the floor with coefficient of friction of 0.470. So what's happening? You've got a person pushing a box across the floor. I didn't draw the person. Our given information, we know that the mass is 40 kilograms. The distance is 10 meters. And the coefficient of friction is 0.470. And we want to find work done by the frictional force and work done by, let's just call that the contact force by the person. So what you do need for these some of the times are force diagrams. And in this case, we need the force diagram in order to solve for friction. So you've got weight going down, a normal force going up, contact force going to the right, and it tells you constant speed, so an equal frictional force going to the left. We know that normal force is equal to the weight. We know that frictional force equals mu Fn. So frictional force equals mu times the weight, and because it's moving at constant velocity, this is also equal to the contact force. So my frictional force equals mu mg. This equals 0.470 times the mass, 40 kilograms, times g, 9.8 newtons per kilogram. So this equals 184.24 newtons. That's my frictional force. And once again, because constant velocity, that's also equal to my contact force. So now that we have the force, we can figure out the work being done. Let's start with the work done by friction. That's going to equal the frictional force times the distance times the cosine of the angle between the two. So we know that friction goes to the left, and we know that the box is moving to the right. So the angle between those two, phi, would be 180 degrees. So work done by friction equals 184.24 newtons times the distance it moves is 10 meters times the cosine of 180 degrees. So cosine of 180 degrees is just -1. So -1 times 10 times 184.24 equals a negative 1842.4 joules. Joules. So with 3 sig figs, the work done by the frictional force is approximately negative 1,840 joules. Negative because friction is taking energy out of the system, so that's why work is negative. So for the work done by that contact force, the contact force is applied to the right. The box is also moving to the right. That should be a dashed line. Now let's just draw this again. So contact force to the right, distance to the right, the angle between those two, phi, is 0 degrees. So this work equals the contact force times the distance times the cosine of phi, which equals contact force equaled frictional force, so 184.2 newtons times 10 meters times the cosine of 0 degrees. This equals a positive 1842.4 newtons, joules. Let me erase that. So the work done by that contact force is the same as the frictional force, just positive. So approximately 1,840 joules. That's about as simple as these work problems can get if you're looking at solely work. I'll do one more example where the angle is not 0 or 180, and then we'll get into what it looks like with energy. Okay, so now the second example asks how much work is done pushing a tall box 15 meters with a force of 400 newtons that is applied slightly upward at an angle of 10 degrees from the horizontal. So for this diagram, we have a tall box. It's being pushed on upwards at an angle and it's moving. Our given information. We know that the distance it moves is 15 meters, that the contact force is 400 newtons, and that the angle phi is 10 degrees. And we are just looking for the work done by the contact force. So work by contact force. I don't need a force diagram for this one because I already have the force. There's nothing I really need to solve for. So my work diagram, we have the contact force going that way. The box is moving to the right, and this is the angle phi, the 10 degrees. Work equals FD cosine phi. This equals 400 newtons times 15 meters times the cosine of 10 degrees. And this comes out to 5,908.8, keeps on going, joules, only one sig fig. So the work is approximately equal to 6,000 joules. And this is positive work because energy is being put into the system. So this is how we use the work equations, and then the next video we'll look at how this is applied to what we've been doing with energy and the bar charts.